Hey everyone, so now we're going to talk about the pH scale. Alright, we're going to talk about the pH scale, and later we're going to talk about the ionization constant for weak acids and bases. Basically, we're going to talk about how you can relate the degree of dissociation and use that to find our Ka and Kb as like Ka and Kp, what I told you about earlier. Alright, so when I say pH, it's defined as the negative log of concentration of H plus ions. That's it. So say HCl associates H plus and Cl minus, and say my concentration of H plus is 0.1 molar. So the pH of this solution is going to be negative log of 0.1. That's what it's going to be. Negative log of 0.1 is going to be my pH. And you can calculate this using like log tables and everything. That's not a problem. So this is how you calculate pH. It's like a direct like formula is given, use it, that's all. It's really easy. Now there's something else called pOH. Okay, so pH it depended on the concentration of hydrogen, like the H plus ions, didn't it? But pOH, it is dependent on the concentration of the OH negative ion. So when I say pOH, it's gonna be dependent like this. It's negative log of the concentration of OH negative ions. Say I take NaOH, associated Na plus OH negative, and say this gave me 0.2 molar. So pOH is negative log of 0.2. That's pOH. Now you can find the relation between pH and pOH. All right. So on the pH scale ranges from 1 to 14, doesn't it? 1 to 14. So 14 is the maximum you can get. Now, after studying results, we've found from results that the sum of the pH and pOH is 14. So this is a really important result, guys. You must remember it. pH plus pOH is equal to 14. Now let's talk about an interesting case for the ionization constant of water. Now, like you denote it by Kw. All right. Now, why is this special? You will come to know. Now, let's take H2O and react it with H2O. Alright. Now, so water acts as both an acid and a base, so I can call it as an amphoteric substance. And when I denote this, I'm going to denote it by Kw. Alright. Now, like, don't freak out. Hydronium and H plus, they're both the same thing. It doesn't matter what you write when you write them in reactions. If you add, basically in your reaction, if you're mentioning water, you put a hydronium ion. Otherwise, you put a H plus ion. All right, just don't freak out, guys. Now back to what we were doing. If you want to find the ionization constant for this reaction, my Kw, that's going to be concentration of OH negative into concentration of hydronium ion by concentration of H2O is going to be squared because it's H2O into H2O, isn't it? And these two I'm going to take, they're going to be in liquid state, right? And this is going to be aqueous. So this can be taken as 1 essentially. So when I say Kw is the concentration of OH negative into concentration of H3O or H plus It doesn't matter, they're both the same thing. And this, my friends, is an important result. The concentration of these two are going to be equal all the time. So through experiments again, we found that Kw is Kw is 10 to the power minus 14 m square at 298 Kelvin. So this depends on the temperature. All right. So when you find this, you can use this relation. All right. So let's go back to what we did over here. Concentration of OH negative to concentration of H plus is going to be equal to 10 to the power minus 14. And you can find this for any reaction. Any damn reaction. It's really cool. Like if I take, say, CH3COOH and I dissociate it, I get CH3COO negative plus H plus and I say I know the concentration of H plus, I know my concentration is, say, 0.1 molar. Find the concentration of OH negative ions, because that's going to be there. I don't know how, but it's just going to be there. It's like basically nothing is totally acidic, completely acidic. Nothing is completely basic. It's always going to have some basic character. So when they say what is the concentration of OH negative, they're basically saying what is the basic character. So I can plug this into my formula over here, and I can say, so concentration of OH negative into concentration of H plus is 10 to the power minus 14, right? And 0.1 molar, I'll put that here. So concentration of negative OH negative into 0.1 gives me 10 to the power minus 14. So what's the concentration of OH negative? That's 10 to the power minus 13, isn't it? Yeah, 10 to the power minus 30. And you can see this is an infinitely small value. So the basic character is like very minute, but it's there. So this relation over here is an extremely important relation which you can use to find either the concentration of H plus or the concentration of OH minus if they ask you. Alright? So let's talk a little bit more about ionization constants. Okay? Ionization constants. You can have them for strong acids, for weak acids, and everything. And here's one fact, okay, which you should probably note down or something to be sure of. Strong acids and strong bases, when they dissociate almost completely. Alright, so you can say the reaction is like almost close to completion. But if I say weak acids and weak bases, there they get a definite, like a defined equilibrium state. So when we usually deal with ionic equilibrium, we'll be dealing with weak acids and weak bases. Alright, just keep that in mind. Now, for example, let's go back to this formula which I spoke to you about before. Alpha, the degree of dissociation, is given by the amount of substance that's dissociated divided by the initial concentration, which I've denoted by C over here. Okay, let's take a reaction. Okay, like a sample reaction. H2O plus HX, like X is a halide, a weak halide. So I'm going to take HX is going to be a weak acid, and it's going to dissociate to give me hydronium ions and X negative, right? Now initially I will say Okay, so this H2O is in liquid state, so that doesn't matter. But initially, I'm going to say let maybe my concentration of HX, let's say my initial concentration is C, alright? And then at one point of time, there's no dissociation happening initially, so these two are going to be 0, right? But now, at some point T, at time T, right, at time T, this is going to have some concentration C minus, say, X, and X is the amount dissociated, right, and this is going to be X, and this is going to be X. Because the amount associated is going to be how much of this we get and how much of that we get. Now, I'm going to take that amount associated over here, that is X, and if I want to relate it to alpha, the degree of dissociation, I can write X is equal to C alpha, right? So X is equal to C alpha. I'm going to plug that in back down here. So when I write it, I can write C minus C alpha. X is C alpha. Here also X is C alpha. So C into 1 minus alpha, C alpha, C alpha. If I want to write the ionization constant, the dissociation constant rather, okay, so K of, this is an acid, right, so it's going to be Ka is going to be constant H3O positive into OH negative divided by the concentration of H2O, which can be taken as unity because it's a liquid, and the concentration of HX. HX is in its aqueous solution, so it's in its aqueous solution, so you take its concentration. Now H3O we knew it was C alpha, OH negative C alpha, divided by HX, C into 1 minus alpha, right? This C gets cancelled. So I can say my K of A or B, depending on what it is here, I've taken A, it's going to be C alpha squared divided by 1 minus alpha. And that is an expression to get the dissociation constant if they give you the degree of dissociation and the initial concentration of the thing. So remember, this formula, it can come in handy a lot of times. Thank you. Before we leave, I'd like to tell you give you one more interesting relation between Ka and Kb. Alright. So the relations we've come up till now were that concentration of OH negative ions into concentration of H plus ions, that was 14, right? And pH plus POH was equal to 14. Now you can also find P of Ka. You can get P of Ka, and you can get P of Kb as well. It's a thing. I don't know why is it a thing, but it's a thing. So you can find P of Ka, you can find P of Kb, and again, like P of Ka is going to be negative log of Ka, and P of Kb is going to be negative log of Kb. You can check it out in your book or something, but this is the gist of it. So negative log of Ka is pKa, and negative log of Kb is pKb. And these two are also related. I can say, you can derive it yourself if you want to, it's not really necessary, but I can say that P of Ka plus P of Kb is also equal to 14. Okay, so these are three relations between things, all acids and bases, so you can note them down. These are important, they'll help. Alright, also Ka, there's one more, Ka into Kb is Kw. No, Ka into Kb is Kw, and this is not 14, this is 10 to the power 14, guys, 10 to the power minus 14. And Kw, that's 10 to the power minus 14, so if I So Kw is 10 to the power minus 14. That's one more thing you should remember. Just something to sum it all up before we leave. Okay, so thank you, and I will see you in the next video.